thank you all for coming and sitting through an exoplanet talk at the end of this day full of black holes and extragalactic work. I appreciate it. I'm excited to tell you about some of the things that I think are most interesting and most exciting about what next generation X-ray facilities like AXIS will be able to do for the field of exoplanets. I like to start off my talks with this graphic. On the y-axis, I'm showing the number of exoplanets known as a function of the year, so for the last 30 years or so. And what you can see is that there's been a really tremendous increase in our knowledge of planetary systems outside of our own solar system. In the 1980s and 1990s, we barely knew of anything outside of the solar system. But then starting in the late 1990s and early 2000s, we started this exponential ramp upwards, which has continued into the 2010s and now the 2020s. As a result, we've started to learn lots about what is out there. The early dissections, the ones in the 1980s, 1990s, were primarily large planets that were very massive and very close to their stars. These are the ones that were easiest for us to detect with the instrumentation we had available at the time. But as our technology has improved over the last few decades, we've been able to push to lower and lower masses and more difficult planets to detect. And now our technology has come to the point where we're able to find terrestrial planets the size of and the mass of Earth in temperate orbits that perhaps might even be the right temperature range to have liquid water on their surfaces. And this is really exciting because now, instead of just having to ask questions like, are exoplanets out there, or do planets form commonly around stars at all, we can start to ask questions like, are the planets that are there that we know about anything like the worlds in our solar system? And do they actually have life like we have here on Earth? And we've been working towards trying to answer these goals, and we think we have a pathway to do it. The idea is that we want to take images of planets like the Earth using large telescopes in space. We want to take our thumbs and stick them over the star using a device called a coronagraph and block out the light at the level of 10 to the minus 10 contrast, so we can see something that's 100 or 10 billion times fainter than the host star, about an arcsecond away. And if you do that and you look at our own solar system, this is a simulated image of what you might see. And you can see these three dots. So there's Venus very close to the star, there's Earth a little bit further away, and then there's Jupiter. Then we want to figure out which of these planets might be in this region that we call the habitable zone, which is where we think that planets under the right conditions might be able to have liquid water on their surfaces. Choose one of those planets, stick it on a spectrograph slit, and take an observation to figure out what might be in its atmosphere. This is what we would get if we took an observation of Earth at a distance of about 5 parsecs, and we exposed for about a week with a 15-meter telescope in space. So this is a difficult observation, lots of collecting area, lots of time, not many photons. But what you can see is you can start to see spectral features emerging from this spectrum. So this is an optical near-infrared spectrum. And if you line these spectral features up with the spectral features that we know about having present in our atmosphere, you can see evidence for oxygen, molecular oxygen, and water vapor and methane. And what's exciting about these molecules is that if you just leave them together in a room by themselves for a long period of time, they will no longer stay there. They will react with each other. So in order for these things to be present, they have to be continuously produced. And the way that this happens on Earth is biological. So if you see these species in chemical disequilibrium, like we see on Earth, then you must know that there's something producing them, and that could be a sign of a biosphere outside of the solar system. So this is the goal, this is the grand dream of our field, is to try to figure out, are these biospheres like we have on Earth common? And we think we have a path to do it, but there's a lot of stuff we need to understand and a lot of things we need to fill in the meantime, and I think AXIS can help. So in particular, what I want to talk about today are 3 questions. One of them is, how old are the stars that we're going to search for life? One of them is, what causes some planets to keep their atmospheres and some of them to be totally stripped and made inhospitable? And finally, what are rocky exoplanets made of? And I think X-ray observations are going to be crucial for helping to answer all 3 of these questions. So first, I'm going to start off with the question of, how do we learn how old the stars are that we will search for life? Over the last 4.5 billion years, since the formation of the Earth, the way it looks has changed dramatically. So right after its formation, Earth was Relatively molten. It was still having lots of impacts from comets in the great late heavy bombardment. It still hadn't lost all of its heat from formation. And as a result, there was no life there. It took a while for Earth to become hospitable to life and for life to arise. So if you looked very close to the beginning of the solar system at Earth, you would see no evidence of biosignatures in its atmosphere. Starting about 4 billion years ago, though, you would start to see some chemical disequilibrium starting to appear. So around 4 billion years ago, we have the first evidence for life on Earth, plus or minus a few 100 million years based on our relatively poor understanding of the fossil record back then. The first life on Earth did not look the way it does today necessarily. That life was anaerobic because there was not really any oxygen in the atmosphere. Photosynthesis had not yet developed. So the biosignatures that we might see and that we might expect included carbon dioxide, methane, and nitrogen in diatomic molecular form. Then, about 2 billion years ago, photosynthesis emerged and became common, and this dramatically changed the atmosphere of our planet. We call this the Great Oxygenation Event. So over the course of that few 100 million years, around 2 billion years ago, we went from an atmosphere with relatively little oxygen to one that has about 20% like we have today. That dramatically changed the biosignatures as well. Now, if you look at a spectrum of Earth, the most prominent features include ozone and oxygen, diatomic oxygen. This is all happening well before complex life has become common on our planet. That was only about 500 million years ago when the Cambrian explosion took place. And then I'll put in for completeness, in the last 100 years or so, we've had another change in the way the biosignatures on Earth looks. And in particular, we start seeing evidence of human technology being detectable from outside the solar system. So you can imagine radio signals from TV, radar that we shoot at Venus to measure the size of the solar system. Those are some of the brightest beacons that our species has sent out. Artificial lights on the backside of the planet, atmospheric pollution like chlorofluorocarbons in our atmosphere. These are all potentially detectable by species that have similar, maybe a little bit better technology than our own right now. So potentially we could see all of these different things changing as a planet goes through its course of life. And therefore, we really need to know how old any given planet is in order to put the biosignatures that we detect on it in context. So for example, if we found a planet around a really young star, something like 1 billion years old, that was fully oxygenated, then that would imply that it went through the development of photosynthesis earlier than our planet did, which would be interesting for how fast or slow life proceeds and evolution proceeds in different environments. On the other hand, perhaps photosynthesis doesn't always happen, and sometimes you get planets that are purely anaerobic, and they have biospheres that look a lot like the Archean Earth, the early Earth before the Great Oxygenation Event. If we see something like that around an older star, that might be an indication that perhaps photosynthesis is special in some way, or we were lucky for it to develop on our planet the way it did. So we can start learning about astrobiology if we can learn about stellar ages. Turns out, though, measuring the ages of stars on the main sequence is pretty hard. After about the first few 100 million years, stars don't really change much until they run out of nuclear fuel and evolve off the main sequence. They'll slowly puff up and get a little bit hotter as they burn hydrogen in their core. But that's pretty difficult to tell, and it's difficult to infer ages from that unless you have many, many stars that are all coeval, like, for example, in an open cluster. So how can we take any individual field star in our solar neighborhood and assign to it a precise age? One way that we could do this is using the X-ray luminosity. It turns out that X-ray luminosity traces magnetic field strength in main sequence stars even after it becomes difficult to measure other magnetic tracers like rotation periods if you have a sensitive enough X-ray telescope. Several groups have worked on this, including a couple of my group members most recently. One of them, Naja Alvarado-Quinones, who is a undergraduate at University of Puerto Rico for about another week before she heads off to grad school at the University of Wisconsin, and Sydney Jenkins, who's an MIT grad student. So we've been trying to go through the literature and finding all of the stars that we know that have both measured ages from some other reliable metric and also have measured X-ray fluxes from surveys like ROSAT, eROSITA, observations from Chandra or XMM. And there's just not many of these stars. Axis could be really transformational by observing lots of open clusters, especially the older ones, where we can constrain the X-ray luminosity and how it changes over time for many, many stars, all from known ages at once. So observations of stellar clusters, thanks to Axis's really great point source sensitivity and soft X-ray sensitivity, would be really key for this. Okay, I'm going to change gears now and move to question number 2. What causes some planets to retain atmospheres and other planets to be stripped of their atmospheres? In our solar system, there's not just one planet in the habitable zone. There are 3. Venus is in the habitable zone potentially, Earth is in the habitable zone, and so is Mars. Only one of these 3 planets is habitable. I'm going to focus on Mars here because the reason you can't live on Mars right now is because it has lost its atmosphere. We believe that Mars once had an atmosphere similar to Earth. We believe it once had running water on the planet. We see that in the geology of Mars. Yet, over the 4.5 billion years since its formation, this is no longer here. So why did Mars lose its atmosphere while Earth held on to its? And how can we predict which planets are going to lose atmospheres and which are going to retain them? Beyond just these relatively thin atmospheres that we have on Earth, relative, and compared, in Mars, which no longer has much of an atmosphere at all, atmospheric mass loss is a major sculptor of the planet population, even for much, much more substantial atmospheres, like the ones around giant planets, these thick hydrogen-helium envelopes. So what I'm showing here is a way of visualizing the population of exoplanets that we've detected. On the y-axis, I'm showing the planet radius, how big it is. And on the x-axis, I'm showing the semi-major axis, how far it orbits from its sun. These are all very close-in planets. All of this is well within the orbit of Mercury. And you can start to see some patterns when you look at this plot. So up in the top, we have this cluster of points. These are what we call the hot Jupiters because they are about the size and mass of Jupiter, and they're very close to their star, and therefore hot. We are really good at coming up with names for planets. We also have these sub-Neptunes and super-Earths down here. These are some of the most common planets in our galaxy. It's a little bit surprising that we don't have any in our own solar system. At least we don't have anything intermediate in size between Uranus and Neptune, the ice giants, and Earth, the largest of the terrestrial planets. But about 30% of stars outside of the solar system do have these. And then we see some deficits. We see some areas of this plot that are underdense, where we have fewer planets than average. And this is one area that's called the Neptune Desert. So what's going on here? We believe that what happens is that planets can generally migrate. It seems to be the case that planetary orbits can change quite a bit. So why can't Neptune-sized planets or sub-Neptune-sized planets from further away, where we know that they exist, move inwards into this region? Well, we believe that they do, but then once they get there, they lose their atmosphere. So they start getting bombarded by radiation from the star. The atmosphere dissipates. And when this happens, the planet shrinks because it's losing this thick hydrogen layer, which puffs it up and makes it appear larger. So instead of remaining in the desert, it moves down outside of the desert into this population of stripped cores that are below it. We think that this is a likely scenario, and we actually have some recent evidence. Grad student Sydney Jenkins from MIT is about to submit a paper tomorrow, I believe, describing a planet that we found moving into this desert, migrating there as we speak. So we kind of have some corroborating evidence for this. So how does this actually work on a microphysics level? So when we have this hydrogen-helium atmosphere on the planet, imagine this is, a few hydrogen molecules in this thick atmosphere. If you have a high energy photon that comes in, what it will do is it will ionize one of the hydrogens. You'll have an electron that gets spit off, and then some kinetic energy excess from the photon is delivered, which then is enough to blast that hydrogen out of the atmosphere. It gives it enough escape velocity to escape out into orbit. So you need high energy photons to do this. They need enough energy to ionize the hydrogen, and they need enough kinetic energy on top of that to blast out the remainder of that molecule into orbit. And if you do this commonly enough, often enough, then over millions of years, you can erode these atmospheres and end up with these stripped cores. So we need to understand not just the overall radiation environment, but in particular the high energy, the X-ray, and the extreme ultraviolet radiation environment to predict whether a planet will retain its atmosphere. This is a spectral energy distribution of the TRAPPIST-1 star. This is a very famous star that has about 7 small planets orbiting it. And over on the right-hand side of this plot, you can see the stellar continuum, this big bulge over around 10 to the 4 angstroms that peaks in the near infrared, because this is a very cool star. But the part that's really important for photoevaporation is this high energy tail over here, which you can access with only X-ray telescopes. The extreme ultraviolet from about 100 to 1,000 angstroms, you really can't access in any other way other than taking an X-ray observation, taking your near infrared or your near ultraviolet observations and using a model to interpolate between them. So if you want to understand the environment, the radiation that these planets get, you have to have these X-ray observations. This is especially important for the low mass stars, the M dwarfs, which, even though they're relatively small and relatively faint, they actually emit a proportionally higher amount of high energy radiation than the sun does. That means that if you want to be close enough to this relatively faint star to be warm enough to have liquid water on your surface, you have to subject yourself to a lot more high energy radiation, potentially meaning that you can't hold on to your atmosphere as well. We can visualize whether a planet is likely or not to retain its atmosphere by comparing its properties to something that's called the cosmic shoreline. This is a concept that was developed about 7 years ago by Kevin Zonley. So this is a graph that shows on the y-axis the extreme and X-ray flux, extreme ultraviolet and X-ray flux that a planet receives. And on the x-axis, it gives the escape velocity from the planet. So it's basically just doing that energy balance. Is there enough of this IXUV flux to blast off all of those little hydrogen particles, or perhaps not hydrogen now, because we're talking about atmospheres more like Earth, so maybe oxygen, other heavier molecules. Or is the escape velocity, the gravity of the planet, strong enough to keep those particles together, even though they experience this high level of radiation? And Kevin drew this green line across the center of the plot, which is effectively the location of Mars. And he said that Mars is right on the shoreline because we know that for a long time it did have this atmosphere, but it's recently lost it. So you can then compare all of these other planets to the location of Mars and say, well, this one seemed to have experienced a lot more XUV than Mars did, and has less of a surface gravity, lower surface gravity, lower escape velocity. So that should definitely have lost its atmosphere, or you can go the other way. So this is kind of a crude, but order of magnitude way of predicting whether a planet should have an atmosphere or not. It turns out that understanding this and making this kind of prediction really depends a lot on our precise knowledge of the X-ray properties of the star. So here's another way of looking at this. This is a plot made by Emily Pass, who is a Torres Fellow at MIT. And what Emily's done is she's basically taken exactly the same points from the Zonley paper, the original paper that laid out this concept. And she has focused in on the planets that happen to be orbiting the lowest mass stars, these nearby M-dwarf stars. And Emily's thesis involves studying the X-ray properties and the activity properties of those stars. And what she did was she said, well, let's take this new understanding of the history of X-ray flux that these planets will have experienced, and let's see what that does to their location across with respect to the cosmic shoreline. And what she found is that they all move upwards into the area of the plot where it's harder to retain atmospheres. So if we don't understand how the X-ray flux has changed in the history of these planets, if we don't understand what this environment is like, we can't predict whether any given planet will keep an atmosphere or not, which is really important for understanding which planets are actually good places to live. We want to do this. What Emily did was a very good first pass, but there's a lot of uncertainty still in these observations. We especially don't know much about the X-ray history of the very lowest mass stars, the ones that are just barely above the hydrogen burning limit. So it would be really great to take observations again of these low mass stars with next generation facilities like AXIS. AXIS is great for this again because we're looking at these point sources with relatively soft spectra. And trying to fill in the history for all of the stars, even the ones with the very low mass the very lowest masses that we can't necessarily detect because their overall luminosities are so small with existing facilities. Okay, I'm going to change gears one more time, and I'm going to talk about how can we learn what elements and minerals rocky planets are made of. So the composition of a planet, the things that make it, the minerals and the rocks that make it up, are really important for predicting how a planet's going to behave. So for example, it turns out that the ratio of magnesium to silicon is a really important indicator in determining how long plate tectonics will last on a given planet, because this ratio determines whether you produce a mineral called pyroxene instead of a mineral called olivine. These minerals have different heat conduction properties and different viscosities, and as a result, if you have more pyroxene than olivine, if you have more magnesium than silicon, you'll eventually have longer lifetime of magnetic fields and plate tectonics than we do here on Earth, which means that potentially these planets can last longer and remain hospitable longer because our magnetic field protects us against atmospheric loss as well. Another important example of why we want to understand what planets are made of is because it's not necessarily the case that if you see disequilibrium chemistry in an atmosphere, it must have come from biology. You could have, for example, outgassing of oxygen from rocks on the surfaces of planets. If we don't understand what the planets are made of, we can't understand whether it's likely or not for oxygen to be outgassed. So if we understand what the geology of planets typically in the solar neighborhood is like, then we can decide whether or not any given signature of a possible biological detection that we see is really due to biology, or if it could just be some weird geological feature. So it's good to know what planets are made of. How do we do this? It turns out it's really hard. Our exoplanet observations are almost all indirect, and those are the ones that have been the most commonly used and the most successful today. We've learned a lot from them, but we only get bulk properties, mass, radius, orbital elements, mostly. So how can we learn about these compositions? Well, if I want to find out what a rock is made of on Earth, what I do is I take a rock and I crush it up, and then I take it into a lab and I put it into a spectrometer. It turns out that this is a little bit more difficult to do to a planet and perhaps less ethical. Uh, so instead, what we're going to do is we're going to let white dwarf stars do the dirty work for us. So white dwarfs are the burnt out cores of stars like our sun after they run out of their nuclear fuel. They're very dense. They have typically half the mass of the sun, but it's all packed into a radius about the size of Earth. So the mass is about 300,000 times greater than Earth. As a result of this extreme density and therefore extreme gravity, white dwarfs are chemically stratified. The lightweight elements like hydrogen and helium float to the surface, and the heavier stuff sinks to the core. So if you look at a spectrum of a white dwarf, its atmosphere should only contain hydrogen and helium. And indeed, that's often what we see. Here's an example of a beautiful hydrogen-dominated white dwarf, which shows only the Balmer lines and nothing else in its spectrum. However, sometimes you can get new stuff that has recently fallen onto and accreted onto white dwarfs, and that can show up in the spectrum as well. And what's nearby to many stars is planets and planetary material, asteroids, comets, minor planets, and even sometimes major planets, planets the size of Earth or maybe even Neptune in our solar system. So the idea is that after a white dwarf evolves off the main sequence, most of the planetary system should remain intact, but dynamical instabilities can exist. And if you happen to have a dynamical instability that kicks something like Ceres into a very eccentric orbit that has a close approach to the white dwarf, you can end up tidally disrupting that object, breaking it up. It then grinds down into a disk, which then streams onto the surface of the white dwarf. And when you get this new gas made of rock that's on the surface of the white dwarf, you'll start to see the elements that make up the rock. So you can start to see elements like nickel, iron, calcium, magnesium, silicon, all of the basic rock-forming elements that we see here on Earth. And we can use this to learn about what these planets were made of even outside of our solar system. It turns out that Pluto white dwarfs have shown lots of diversity in the kinds of things that we see in terms of geology. We see things that are very similar to the solar system, but we also see some weird objects, some weird outliers. So if we want to understand in general what these planets are made of, we need to be able to make these comparisons. One main challenge to doing this is that heavier elements sink faster than light elements do in the surfaces of white dwarfs. And that means that in order to back out what that planet was made of originally, we need to understand the accretion history. So here's what I mean by this. So imagine I have a white dwarf atmosphere that has oxygen, which is a lightweight element relatively, and iron, which is a heavy element relatively. The iron is going to sink out faster than the oxygen. And when you do that, you're going to have a period of time where there's a lot more oxygen than there was iron, even though there was originally a lot of iron in the body. So let me show this again. Imagine that we only have oxygen and iron, and it all came in one burst. It fell onto the surface of the white dwarf all at once. If we take a snapshot at some period of time, we could see it where there's only oxygen in the atmosphere, even though they're started off with iron as well. So you can actually skew the abundances that you measure towards the lighter elements if the accretion was all episodic, if it all came at once. However, if the accretion is constant, if it's active, then the abundances on the white dwarf are going to be more similar to what they were in the original body, because you're going to be constantly replenishing with these heavier elements. So we need to understand what the accretion history is if we want to be able to make these measurements precisely. X-ray observations are the way that we can break this degeneracy, because if we observe with X-rays, we can measure the accretion rate independently and say, right now the accretion matches what we infer if we believe that this is coming in steady state. Or there's no accretion right now, yet we see this material on there, it must be decaying away. It must have come all at once and no longer is happening. If you know that, then you can make the correct assumptions, back out the correct elemental abundances from your model. So far, we've detected X-rays from one source that's published, and when I say we, I mean Tim Cunningham, who is a Harvard postdoc, a Hubble Fellow at Harvard. So Tim has detected X-rays from one source, and as another one that's on the way that's not yet published yet. And that's just because these are really faint X-ray sources, and they're very soft. This is basically pushing the limits of what we can do with existing facilities like XMM and Chandra. But with Axis's much better sensitivity, we'll be able to do these measurements routinely. And this will be something that we can check for every white dwarf that we want to make these inferences for and learn whether the accretion really is coming on constantly or if there are these spikes that we need to correct for in our measurements. All right, so with that, I think I'm out of time, so I'll put my conclusions up. Axis is going to be great. It'll help us learn about how to measure the ages of planets, how to study extrasolar geology, and learn about atmospheric mass loss. Thank you.
We have time for a few questions.
Hi. So one of JWST's more interesting immediate results was that planetary nebulae have these interesting structures, and in particular, they have layers that indicate that the outflow process was episodic rather than steady. Could that be used to do some of this assessment? In other words, could those shells contain a history of the deposition of these heavy elements?
That's a great question. I think probably not these particular white dwarfs. And the reason is we have to wait until the white dwarfs have cooled to about 25,000 Kelvin in order to make these measurements. Above that temperature, number one, their lifetimes are not that long, so you could still have heavy elements in their atmospheres that were primordial. They haven't sunk down to the center yet. And also you can get radiative levitation of materials when you have these really high luminosities, so you can have heavy elements that are brought up, not by, are brought up, not brought from above onto the surfaces. So you really want to look at the cooler white dwarfs that are maybe 100 million years old or so before you can make these inferences. That is a great question, though. It would be interesting to look at the white dwarfs that come with these planetary nebula and look at the signatures there and see if we can develop any patterns and see if we can make inferences from the physics we learned from there and then apply it to these cooler white dwarfs that have long since lost their planetary nebula into the interstellar medium. So yeah, I have to think more about that, but that's a really great idea. Thank you.
Okay, maybe a quick question if anyone has one.
So it's not actually an X-ray question, but from early on in your talk, you showed how the Earth would appear to a distant civilization. So some time ago, there was a lot of discussion about like the red edge and how that could be a biosignature,
Yeah.
from from the signatures of chlorophyll.
Mhm.
And I didn't see any of that in that spectrum. So has that discussion of the red edge being a biosignature gone away, or is it still in play?
Yeah, that's a great question. I wouldn't say it's gone away. I think that there are other ways to make red edges. And usually people now think of the spectral features as more robust, but of course more difficult to measure because they're much narrower in bandwidth. So it could be useful in like a first pass, take a photometric point and then look and see like, oh yeah, is there a red edge visible in the photometry? And then come back and bring in your spectrum and spend a week taking a spectrum of that planet before you waste all that time on a planet that's totally desiccated anyway. Exactly, yeah.
Okay, let's thank Andrew for the talk. Next up, we have Tansu Daylan, if I say your name correctly, telling us about the AXIS search for transiting planets around young white dwarfs.
Go full screen. Yeah. Thanks. Great. Thanks, Mike. Hello, everyone. I'm Tansu Daylan, Assistant Professor of Physics at Washington University and a faculty fellow at the McDonald Center for Space Sciences, and also a member of the Access Science team. So it's great to welcome you all, and thanks for being here and participating in the conference. So I will highlight two opportunities that I think are very important that I think Access will be able to address regarding exoplanet research. And one of them is essentially the title. The other one is, I will only cover very briefly in my first slide, because it actually went into section D of the proposal. So you can probably check that out to learn the details. So this is collaborative work, essentially with the Stars and Exoplanets Working Group, essentially Leah, Kevan, and the other Access Science team leadership. So the first problem that I think Access is going to address that I want to highlight very briefly is essentially explaining exoplanet demographics. And the other one that essentially is going to be the rest of the talk is doing so and essentially across stellar age, which is not something you immediately think about when we discuss exoplanet demographics. So let's jump into it. First, I want to highlight essentially a result that I'm pretty sure you're all familiar with, which is that Kepler Space Telescope has characterized the so-called demographics, or more technically, occurrence rate of planets, small planets, across stellar types, especially from Sun-like to M-dwarfs, and recovered this so-called demographic feature called the Fulton gap, that essentially says that planets that would normally exist very close to their stars around Neptune size, as well as those that are in between super Earths and sub-Neptunes, are underabundant. And we would like to understand why, because there must be physics that's carving out this demographic feature. So essentially, the most important idea out there is the photoionization, where basically these planets are being bombarded by extreme UV and X-ray photons, which then ionize and cause hydrothermal escape, so that these planets essentially lose lose their mass, and then evolve in the so-called irradiation radius plane. Now, Axis will be able to do this using soft X-rays because we think that especially XUV variability, CME events, coronal mass ejections, as well as flares are causing this photoionization. There's also another alternative hypothesis, the core-powered mass loss, and we would like to distinguish those two to basically understand which one operates more often than the other. As part of this, I also want to highlight flares and flare searches. Counting flares across stellar ages and types is also important, and it will also be addressed by Axis. So this is work that already went into section D of the proposal. So basically, I will skip this, just highlighting the fact that I'm also excited about that. Now, coming back to the actual topic, which is white dwarfs, I think one of the major issues in the exoplanet research that we don't usually discuss is contextualizing, or rather putting Earth in cosmological context across stellar ages. And this actually includes post-main sequence as well. Because if you just think about main sequence or subgiants or giants, asymptotic giant branch, we are basically missing essentially half of the picture, because when stars go post main sequence, they may retain some of their planets, or other planets may form, and we would like to understand how the Earth would sit in this bigger context as the sun will evolve out of main sequence. So I unfortunately don't have a telescope to show you a picture of white dwarf, but instead I'm just showing a picture I took during the solar eclipse last year, where we drove down with several faculty colleagues to give a talk about 2 hours of south of St. Louis. So in this picture, you're basically looking at, well, first the moon eclipsing the sun. If I zoom in, you'll see the moon first, and let me actually zoom in a bit more. So this is our sun. So right now what you're looking at is essentially the photosphere. The photosphere is unsurprisingly has a radius of 1 solar radius. What we typically don't think about when we think about the sun is the corona around it. So this corona has very high energetic particles, especially the electrons. They have a Maxwellian distribution, and then when they collide, they produce Bremsstrahlung radiation. And this is soft X-rays. So essentially, a good fraction, about one part in a million of sun's brightness actually goes into soft X-rays, and this is essentially because of this optically thin emission that is radiated from essentially the corona, which has a big solid angle. If you think about it, it extends to about 5 to 10 times the solar radius. Now, this is also true only to a certain extent for white dwarfs. White dwarfs are very hot usually, unless they have enough time to cool, which means that they actually don't have a lot of convection, and as a result, they actually don't have as much of a corona that sun-like stars do. But still, they can be much hotter, in which case even their bolometric luminosity can be high enough for us to detect them in X-rays. They also have a very complicated story about cooling. I won't go into detail, but they basically normally start at the top left of this, post AGB, go down. As they do so, as you can see, these are the least massive white dwarfs. These are the heaviest ones. So because they are degenerate, the radius mass relationship is upside down. So the heavier they are, the smaller they get. So normally they move down, I guess, left and down here. There's this Q branch that was recently discovered by Gaia, which essentially predicts that a fraction, about 10% of these white dwarfs, get stalled in their cooling as they go through this Q branch. So some of the white dwarfs can actually be much older than you would normally think, just based on the crystallization cooling timescale that is predicted. This is important when we contextualize planets in the life cycle of a white dwarf. Now, here comes the planets around white dwarfs or orbiting white dwarfs. Now, Andrew just gave a talk and managed not to highlight WD 1856, so I will just do that. So this was work led by Andrew that I contributed, where we basically discovered this object using TESS. This is not the TESS light curve. It looks worse in TESS. But basically, we now know intact planets around white dwarfs. The next order question is, what is their occurrence rate? We would like to better understand this. And I think X-axis can definitely help us answer this question. So axis will be sensitive to down to about 10 to negative 16 erg per second per centimeter square if you expose for about 20,000 kiloseconds. Once upon a time, I gave a talk to a mixed audience of astrophysicists, and they were mostly working on black holes, and I made the mistake of using the term supermassive Jupiter. So I know that these scales can be very relative, so I just want to get the numbers right for the good fraction of the audience. So white dwarfs can be much smaller, about 1% of the sun. And as a result, they can be much fainter. And in fact, the fraction of the X-ray luminosity to their bolometric luminosity is even smaller because of what I just mentioned, that they don't actually have a corona. Still, those that are relatively hot, either because they're accreting, or they just went through the COUP range, or they just merged, or essentially they're just hot. They just came out of the AGB post-main sequence evolution. If either of those are right, then they will actually remain bright enough in soft X-rays from 0.2 to about keV or so, and they'll be axis detectable, and that will have very important implications. Now, this is very detailed, and I don't have time to go into what a transit really looks like. They're typically V-shaped, but that does not have to be the case. Typically, we are looking at a very short event. These are of order 200 seconds or so. If you go down to about 100 seconds, it becomes way too short because you're approaching the so-called Roche limit. So you no longer expect intact planets to exist at those orbital periods anyways. So typically, it's either 200 seconds or even longer. If it's really long, then you wouldn't expect repeating transits, because typically the way we think about axis is the observations will be of order a few hours to a day or so. So if you want repeated transits, then you would basically be constrained to orbital periods of order a day and even shorter. But you don't want to go too short, because you'll then be not even expecting intact planets due to the Roche limit, which is of order 1% of an AU for a typical white dwarf. So this has been basically, by the way, an important thing. So because this is very short, again, a few hundred seconds, you don't have a lot of exposure time to get these photons. So your target needs to be bright, typically brighter than about 10 to negative 13 Hertz per second per centimeter square. This may look really challenging for you, and it is, but there's definitely enough targets on the sky that came out of the DR3 Gaia results, and we currently have a target list of about 1,000 that we could point an Axis-like mission to actually do this science. And on top of that, there is the new population of white dwarfs that could be discovered through the Galactic Bulge Survey, where this could also be done. Now, part of this would be just serendipitous in the sense that AXIS is going to essentially, its primary mission will be, it's an agile telescope, so it will be hopping from pointing to pointing, but when it does so, the M dwarfs and the other serendipitous white dwarfs in the field will also have light curves that we could use as a essential auxiliary science to search for such transits. And this is basically again, I mentioned that we have an underlying catalog where we can actually do this. The other one is the Galactic Bulge Survey that I alluded to, which is going to be very exciting for any science you do with stars and exoplanets, especially transiting exoplanets, because it will be cadenced. So we will go back to the same field once every 6 months, and you will be able to essentially do what we did with TESS, just at a very different cadence, I guess, as well as brightness level in a different wavelength. But it will be essentially, it will allow us to look for periodic transits or transit-like events, which will include transits of white dwarfs. Again, we will also be sensitive to other types of transits, which I don't have time to go into details, but as an example, there are other X-ray transit or planets that are transiting that have been detected in X-rays. Typically, they have brightness of order 10 to negative 13 ergs per second per centimeter square. So a couple of things to highlight. Axis will have a lot of synergies with LSST and Roman to do this. I won't go into details. Axis will have a particularly high contrast to achieve this because, again, white dwarfs are particularly bright in soft X-rays, especially if they're hot or, as I mentioned, satisfy one of these criteria. And the extended observational baseline that was recently made available by going to L2 will particularly advance this science case as well. So let me just put my conclusion slide and take any questions. Thank you.
Okay, we have time for maybe one question.
So I still find it a little difficult to understand how these planets survive the AGB phase. So how common would they be? I mean,
Okay, so
having
they
found a few doesn't mean.
Right. So the occurrence rate must be really low. The question is, it's zero or not? And it's probably not zero. We have evidence for it. But basically, to address your question directly, these planets would have to migrate in. Now, as a planet loses its half of it, so sun-like stars will lose about half of its mass during the post-main sequence evolution. And during that phase, obviously, the planets will go away because the system is losing mass through Kepler's third law. So as they do so, they might essentially cross certain mean motion resonances, and that can destabilize the system. So in general, doing so will cause most of the systems to essentially to lose all of its planetary content, but not all of them. And especially if you have planets that can later migrate in, and we think WD 1856 is an example of that, then you can definitely have planets transiting white dwarfs that are intact and certainly outside of their Roche limit.
Okay, thank you.
That was a beautiful simulated light curve that you showed with the transits. How many white dwarfs will get data that high quality?
Only a few, yes. So that was, I believe, 10 to negative 13 ergs per second per centimeter square. Only a few, but obviously you don't have to go that good in order to detect them. There, you can detect individual transits, which you don't have to. Yeah.
Okay, let's thank Tansu again. Next up, we have another invited talk by Eric Feigelson, telling us about young stars and star formation with Axis.
Thank you very much. It's a pleasure being here with your really exciting Axis proposed mission. My congratulations on developing such a fine instrument. I'd like to talk about a topic that is not in classical X-ray astronomy. Normally, star formation is considered the venue of long wavelengths, like infrared and millimeter, and young stars themselves are just usually red in the optical. But in fact, it ended up sort of by strange situation that X-ray imaging telescopes of high resolution and high sensitivity can really learn quite a bit about early stages of star formation and young stellar evolution. So the work I'm going to describe is mostly at Penn State. Konstantin Getman, Costa Getman, is my close colleague. And we had another colleague named Lisse Townsley, who tragically died of cancer a few years ago. So I'm going to feature mostly their work, but there's others as well at Penn State and others around the world. Please be aware, we're not the only group doing this. There's a particularly strong group at University of Palermo in Sicily, and others as well, which I'm just going to ignore for lack of time. So the projects I'm going to mention are typically Chandra imaging projects that each of them occupying 1 to a few million seconds of exposure over 25 years of the Chandra mission. And they've generated dozens of papers that generated thousands of citations. And often these works were in collaboration with other space telescopes, particularly Spitzer, and then Gaia, and now beginning Webb as well. But you can see that Lisse was particularly good at acronyms. So we have a lot of acronyms. COUP and is Chandra Orion Ultra Deep Project. CCCP is Carina Complex. MYStIX is a survey of the whole galactic plane, not the whole plane, but objects further out in the plane. MYStIX is sort of almost complete of all the major star-forming regions in the without 2 or 3 kiloparsecs. Sphinx, star formation in nearby clouds, and T-Rex, you're going to see, is the latest one, going out to 55 kiloparsecs. You can guess where that is. And Missing Links is trying to go a little older in stars. So you don't need this slide because of who you are. You're all expert, but this is the ACES instrument developed at Penn State and MIT in the 1990s. On the right. Got it. This is the ACES instrument. Seen on the right, everything I'm going to show you is the 4 CCD imaging array that subtends 17 arc minutes. Please. And of course, Chandra had a very peculiar orbit, an elliptical orbit that went third the way to the moon. But the marvelous thing about Chandra, of course, was the arc-second mirror. Very heavy, took years and years, $100 million to polish the mirror, very difficult. And my congratulations on your mirror, which is much lighter weight and much wider field of view, although not perhaps quite as high resolution in the very center, but it's a very brilliant mirror, so my congratulations. So also the CCD detector had almost no noise.
Yeah, here, let's see.
So that essentially every photon is a real photon almost entirely. So we can detect stars down to 4 photons in a week's exposure because there's no noise in these X-ray CCDs, at least the one that Chandra had. Okay, well, we will live with this. Thank you for trying. This is the Chandra Ultra Deep Field, and I believe, if we're lucky, I can make a movie out of this. Let's see. Yes, okay. So this is a 13-day, think of 2-week exposure. We're going to zoom in. I'm going to count off the days. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 days. Okay. Every single source in this image, except for the O star in the middle, is variable. And the variations are huge and just sort of, I mean, unless you happen to be familiar, they're really unbelievable. So the one on the upper left is a protostar deeply embedded in a molecular cloud behind the Orion Nebula. And you can see orders of magnitude variations on timescales of tens of minutes and flares lasting tens of hours afterwards. The gaps, again, are different 2.3 day orbits. The instrument is turned off when it enters into the magnetosphere. The brightest flare you saw in the movie is actually in the upper right. And that was one of the brightest X-ray flares ever seen from a normal star in the history of X-ray astronomy. And it just appeared sort of randomly in the Orion Nebula. The bottom one is an example of sort of an astrophysical interpretation the flare starts off in the lower left, so I guess the green part, and it gets more luminous. That's the emission measure on the abscissa, and hotter. And then it climbs up and gets even hotter and then slowly cools. And this U-shaped pattern is there in solar flares. And a single loop of a combination of radiative and conductive cooling explains this. It's the Fabio Reale model from Palermo, if you happen to want to know. It's an old model, and it actually seems to explain these flares remarkably well. But what we're seeing here is orders of magnitude stronger than anything seen on the sun. So pre-main sequence stars, of course, are just formed, and they're formed with disks, and the disks are going to form planets. We've heard from Andrew and others about the planets. But for the first few million years, roughly 5 million years, 3 to 5 million years, the planets aren't there yet. It's a disk of gas and dust. And there's a lot of interest in studying planet formation. For instance, James Webb Space Telescope spends a lot of time looking at these disks. But the disks are now being irradiated by millions of these violent flares from the star itself. And that basically was not realized by infrared astronomers or optical astronomers who don't see the magnetic activity hardly at all. And really it shows up mostly in the X-ray regime. So the question, and it becomes a fascinating question, then what effect do the X-rays have on the planet formation regime? And the answer is they're probably important in photoevaporating the older disks. And they may be important in other effects. For instance, there's certain signatures in meteorites, the oldest, most primeval meteorites, of something called beryllium-10 and a couple others, which are spalogenic, which probably represent the coronal mass ejection protons and neutrons associated with the X-ray flares hitting the solids of the solar nebula. But it's largely theoretical what effect it has. It could actually affect planet formation itself. Now, this is now a statistical study. This one came out of the MYStIX survey. Again, 20 papers and millions of seconds of observation. And what we're seeing here then is in the color part of this, in the upper right, you're seeing the actual observations. Okay, so the actual flares, sort of statistically counting them, the ordinate is flares per second per star per year. So we actually see 0 to 1, it's a log. So basically a few flares per star per year from different stars, and it's a mass-dependent, mass being the mass of the star. And Chandra actually sees these in the pre-main sequence clusters. I'll show you a couple pictures in just a couple minutes. The dashed lines are extrapolations to lower luminosities, which Chandra basically just doesn't get enough photons to see. But Axis will. The Axis will go an order of magnitude deeper in the flares, and therefore will teach us and see. If we already see of one flare per year, Axis will see several flares per year per star. In these from thousands and thousands, we actually have 40,000 pre-main sequence stars. If you happen to follow a certain literature that the Kepler satellite found some superflares in older solar type stars, it's actually orders of magnitude down, both in frequency and in luminosity. And the entire sun, all the flares of the sun are in the lower left of this diagram. So we're looking at roughly 3 orders of magnitude in power and 3 orders of magnitude in frequency, 6 orders of magnitude more X-rays coming out of a star during the first few million years of its life. So it's really, in the sense of stellar activity, this is the most impressive phase of stellar activity for solar type stars in their lifetime. Okay, so now we're actually looking at some pictures, and now you can think in your mind what Axis is going to see. Each little square there is 17 arc minutes. And notice that the star formation regions are almost all too big for one exposure, so we sort of clumsily mosaic them together with Chandra. This is going to be much, much nicer when Axis does it. And Chandra has a very, very bad deterioration of the point spread function at the edges of those fields, and Axis is not. So Axis is going to have a flat sensitivity, or almost, and it's just going to be very impressive. And so what you're looking here in the yellow dots, those are the Chandra sources. And just for scientific interest, the red little symbols, those are the Spitzer sources. And sometimes, very often, when there's a Spitzer source, there's usually a yellow dot inside of it. Okay, so the Spitzer is seeing the disks. Spitzer doesn't see young stars. It sees protoplanetary disks. Chandra sees the young stars irrespective of whether or not there's a disk now, or there was a disk a few million years ago and it's now gone. So Chandra is the best source of the census of stars that are born in molecular clouds in our Milky Way. And these are just 6 out of some dozens of fields. They're not all this rich, but some are even richer than this. So just for your interest, the Rosette Nebula is there, the Lagoon Nebula, the Eagle Nebula, M17, known as the Omega Nebula. And there's right now, we're involved in a James Webb Space Telescope study of this one that's in the middle, in the bottom, NGC 6357. I think it's called the War and Peace Nebula. I'm not sure. Anyways. So the Carina complex that was really organized by Lisse Townsley is, you can see how many of these is 17 arc minute squares. So they're relatively shallow. Each one's roughly a day exposure. And you can see immediately, I should call it egg crate. It looks like, that's not real, okay? That's because the sensitivity is greatest in the middle of each one of the exposures. And then you get this sort of boom, 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 boom bumpiness that's completely instrumental in origin. But there are about 11,000 Carina members. There are actually 1,000 quasars probably as well. And then there is this orange stuff. And the orange stuff is actually diffuse emission. And in most of these regions, the diffuse emission is, I'll show you a slide in just a second, precedes the supernova remnants. But Carina happens to be an older region that's tens of millions of years old, probably. And it's already had dozens of O stars that are now missing, and that they've gone supernova. And you should just know, if you're just curious, the pretty supernova remnants that are famous in X-ray astronomy, like Casset and Kepler, that are round and beautiful circular, those are the exceptions. I mean, they're from runaway O stars. The most common supernova is in the 19th out of 30 of them in a region like Carina. And it just makes this mess. It's not very pretty, but that's what a supernova remnant really looks like most of the time. And several of the stars that you're looking at in here are going to go supernova soon, particularly one called Eta Carina. Now, this one is a new picture. This is just published a few months ago after Lisse passed away, posthumously sort of worked on by my infrared astronomer named Matt Povich and others. This is 2 million seconds of one field. You can look at the edges. You see the green edges around. So it's rotated around because Chandra now can't stare very long in one direction at a time. So it's 2 million seconds spread over a couple of years. And this is now in the Large Magellanic Cloud. And this is known as 30 Doradus, also the Tarantula Nebula. You might notice in the lower right, this rather blurry thing. That's blurry because it's on the edge of the field. But that's supernova 1987A. That's the one that just went supernova. And this sort of, there's a blur in there that's actually the richest cluster of young stars in the entire local group. It's completely unresolved with thousands and thousands of stars. Now, what it ends up that Chandra is only sensitive to the most sort of higher mass end of the initial mass function in all these regions, really. So it's missing most of the stars. It really sees, let's say, 1 solar mass. Maybe in some of these, it goes down to half a solar mass, just depending on the exposure and the distance. But here, that means if we're seeing 3,615 sources here, okay, there's really hundreds of thousands of them in the field, most of them undetected. And there is also supernova remnants. You can see some of the circles around and shapes. This is a remarkable, complex field, and the Large Magellanic Cloud this is the richest one, but it has other regions that are just totally fabulous. Also, it's not obscured by the foreground. Spiral arms don't obscure the region, and you can just see them optically, and the soft X-rays penetrate easily. Notice again, I'm reading it from the upper left annotation here. Roughly half of them seem to be constant in these exposures, but half of them are come and go. Now, let me see. Half of them are there only in some exposures. Almost all of them are variable one way or another, and these are only seen when they have very, very powerful flares. Again, these are the powerful flares that are rarer but more luminous, and we have not yet analyzed the flaring of this sample here. Oh, I'm sorry. So this is still sort of research in progress. Okay, so I've given you a little bit of a sense of the point sources, but there's also diffuse emission. In this case, it is probably a combination of supernova remnants and shocked O-star winds. This is now a Voronoi tessellation of the region, and the spectra around the edges are different tiles, and they're totally different from each other. The spectral signatures of these regions is totally bizarre. Again, these are CCD resolution spectra. So this is very similar to what you will get with AXIS, but the complexity of the line emission and the continuum as well is remarkable. And one of the things that is Lisse Townsley discovered in these regions is the rare charge exchange lines, because the X-rays hot plasma is adjacent to molecular emission. There can be the unusual physics of charge exchange that hitherto had been seen mostly in the heliosphere and not cosmically. So there's an entire field of science regarding the diffuse emission. The technology of subtracting out 3,615 point sources and then studying just the diffuse emission around them is a very difficult technology. Only Lisse Townsley and Patrick Bruce, her colleague, were able to do this well. And took years of software development, data analysis, sophistication, to be able to take these spectra in the presence of so many point sources. So that, in fact, leads me to one of the lessons. Okay, now I hope you forgive me, Chris and others here. I'm sort of an old timer, okay? My personal heritage goes back to analyzing Uhuru data when I was an undergraduate, okay? So I've worked on 10 satellites over 50 years almost. And so I'm going to give some advice. Okay. Part of my advice is don't assume that standard methodology for analyzing data is going to give you the rich science that you want to acquire from AXIS. It may be fine for many purposes, but if you want to do more difficult things, you need to spend years having software engineers and technical scientists develop methodologies. So one of them was ACIS Extract that was developed at Penn State over, again, years. of work with maximum likelihood and local backgrounds and Poisson probabilities and photons extractions with local point spread functions and photon pileup treatments, then absorption corrected luminosities for very, very faint sources and probabilistic matching of X-rays with infrared sources and naive Bayes classifiers and Voronoi tessellations, which I just showed you in the other picture. And that's just an example of the more sophisticated methodologies that were needed for these kinds of scientific things. And the results were real. Okay, well, this is deep inside. This is from Michael Kuhn's thesis. Deep inside one of these MYStIX technical papers, we had 7 papers just on MYStIX technology, not even on the science. That if you ask the Chandra source catalog, which is sort of standard, what are they called? Threads, I think they're called, software threads. They found 410 sources in some region here. The PW detect and wave detect were developed at SAO in Palermo, and they found 518, and we found 1,019. And since we know the infrared counterparts, we know that 80% of them are right. And so exactly having better technologies to deal with these difficult problems of crowded fields, complicated backgrounds, and complicated mosaics really does transform the science. And don't assume that standard, I'll just make it up and say, Chow threads and Helisoft software is sufficient for your scientific goals. Now, I think this is the most important slide of this talk here. When we started, this is just personal, okay, I remember thinking, okay, we're going to use Chandra and we're going to do a census. We're going to look at Orion where the stars were known and use it as a template. And then we're going to apply it to these other regions and get a census of the total population of pre-main sequence stars, the X-ray luminosity function. And I just viewed that, well, we'll just do astronomy, okay. Then we discovered a new Orion-like cluster in a molecular filament that nobody, well, I guess IRAS had a source, but no one knew it was there. We actually discovered new clusters that nobody seemed to know about. Then we started tracing the structure in the molecular cloud of inhomogeneous star formation at different times in different places, clusters, small and rich clusters, sort of pop off over millions of years. Costa studied triggering of star formation in something called bright rim clouds. He then, and others as well in Palermo and elsewhere, studied X-ray flaring and those U-shaped flares, structures in the temperature intensity diagram. And that led to flare loop and flare physics. Then we've been trying, both Palermo and Penn State have been trying to find the transition between this very, very magnetically active phase of the fully convective Hayashi tracks, known as the alpha-2, alpha-squared dynamo, to the more conventional, sort of softer and sort of gentler rotation-related alpha-omega dynamo that the sun has. We're sort of, I would say we haven't really found the transition convincingly yet, but we're looking. It should occur around 10 to 30 million years, and it's hard to find a good sample to do that. I've already mentioned X-ray irradiation of the disks, but the disks go away. Remember, most of the yellow dots didn't have red circles around them, so that means the young planet is being irradiated, and not just by a continuous X-rays, but by the 100 million of these flares as well. And that science has not yet been done. The effect of flare, of incredibly intense late pre-main sequence flaring on protoplanets' atmospheres has not been done yet. It's quite possible that all the inner planets are stripped of their primordial atmospheres by these flares. It's not clear how much, but it's faster than is usually calculated. Lisa Townsley personally, I think, discovered the birth of the hot interstellar medium from O-star wind shocks and discovered that the H2 regions, which date back to the 1930s, H2 regions with Stromgren, remember Stromgren spheres? It was all wrong. H2 regions are not filled with 10 to the 4 degree gas. They're filled with 10 to the 7 degree gas, and 10 to the 4 is just on the edge. Costa Getman found an age chronometer Andrew, you mentioned the ages of stars. We have one, but you're not going to be interested. Only works at 0 to 10 million years. But we have, and he found age gradients in star cluster formation, which is quite dramatic in its effect on implications for cluster formation. And on and on and on. In other words, we didn't even know what we were doing when we started. I mean, I only knew this first item in my mind. And over the years, the amount of rich science that emerged, that was just, we just followed our scientific noses and did different things in different years and looked at a data set in different ways and discovered different things. And this is the power of imaging X-ray astronomy. It's really impressive what can be done with Chandra and what really can be done with Axis. So I put a little red symbols there. I'm going to show you just a couple slides of a couple of these topics. Okay, here's a serendipitous one. The one, the underlying picture, a grayscale picture, is Herschel. So there's a rich molecular cloud. There's a very well-known southern cluster of stars over there. But then there's a filament that Herschel found when we discovered that there's a cluster as rich as the Orion Nebula deep inside that filament. Its name is IRAS 0900 09002-4732. That's its name. It has no other name. Okay. No one's studied this actually since. I think people should look at it. Okay. Infrared astronomers should look at it. Oh yes, this is a work by, not at Penn State. This is some work by Kevin Stassen, who I believe is closely associated with the Axis mission. And the issue is that, yes, Chandra and Axis can see the flares themselves, but the question is, do they address the X-ray, the photonic emission? The question is whether you also will get the particle ejection, called a coronal mass ejection, or CME. Now, it happens on the sun. We sort of know that. That's the auroras we see on the Earth's atmosphere, upper atmosphere. But no one really knows if these flares, which are orders of magnitude, these are solar flares at the bottom left of the diagram, and these are the T-Tauri flares, orders of magnitude higher. So we're trying now, Costa Getman and colleagues are trying now to detect the first CMEs from Orion X-ray superflares. So far, I have no comment. We don't have a result yet, but this really matters in terms of the environment of young stars. Here are the age gradients that he found, and let's look at the upper left panel there. Okay. That when you're very close to the middle of this cluster, the characteristic age is much, much younger than as you go out there. And I'm going to try to give you, okay, I'm going to give you some astrophysics, a sense of astrophysics. Okay. The simplest way of making a star is to have a molecular cloud that's isothermal sphere. Okay. And then it's dense in the middle and diffuse on the outside. And by the way, isothermality at 11 degrees Kelvin is actually quite possible. That's something about dust cooling. So then the star should form in the middle first, and then sort of go outward like a rarefaction wave, a star formation wave. And when you do a snapshot later on, the stars in the middle should be older. Exact opposite of what's found. The stars in the middle are younger. And the only way to explain it is some really bizarre stuff. Exhaustion of gas or expansion of superclusters or infalling filaments. And believe it or not, there are star formation theorists who actually like scenario G. Enrico Vasquez Semedani from Mexico, Mexico's leading theorist, essentially, likes scenario G. And so we are actually commenting on this. This is the hot interstellar medium. It's in dark blue there, that Lisse Townsley found, and it's before the supernovae. It's the diffusion emission from the shocked O-star winds that fill the H2 regions. And every single region she looked at, this is her work, the MOXIE survey, she was able to find the dark blue, that avoided the green or the orange, that's Spitzer infrared. So around the cold clouds is 10 to the 7 degree gas, over and over and over again, everywhere in every major star forming region. This was the work of Lisse Townsley. So Axis is really going to be great. Okay, at first it has 2 times the field of view. So it's going to map things much 4 times. You know, you won't have to patch together these stupid little things, and it's not going to have the edge effects that we see. It's going to be 2 orders of magnitude, roughly, more sensitive. So it's going to detect the full initial mass function down to not just above one solar mass. So it will have 50 times more stars, and the main problem is going to be crowding. That they won't be, they'll just be too crowded in some cases. Okay, you're going to have 7 times higher detection and count rates. So every flare that we have 10 photons, you're going to get 70 photons, and that will mean there's much more disk flare physics and better measurement of these effects on the disks and the planets. And I'm a little worried about your contamination by those quasars. I'm sorry, Dr. Brandt and others who were talking about quasars and AGN, but your AGN are annoying to us, okay? But I think we can get around that. Okay. So my last lessons, again, I don't think, Dr. Reynolds, you'll be very pleased to hear this kind of thing, but you get this kind of multifaceted, in-depth astronomical studies by spending 20 years and spending millions of seconds exposing on a given scientific topic. And if you want to get astrophysical insights on all sorts of different aspects of it, you need your science groups to be there for 10 years at least. And you need some theorists. You need to spend $1 million a year to do this. So this is not in most budgets of NASA satellites. For some strange reason, the Chandra mission actually funded Dr. Brandt's group and our group and a few other groups to do these kinds of long-standing studies. And there used to be a program, those of you who are old enough may remember the LTSA, Long-Term Space Astrophysics Program, and they killed it years ago. This is the kind of depth you need to really get into some of these topics here. And also work on methodology. Bring in some statisticians or astrostatisticians. Now, don't just write a pipeline that looks convenient. Think about it and improve it constantly over the years. So that's all I want to say. I'm hoping that you learned something about star formation and young stars in X-rays, and you should just know that I think Axis will be fabulous for this field of X-ray astronomy.
Okay, let's leave the questions to the reception and move on to the next talk and the final talk of the session. Maybe quick, the PI gets the.
I just wanted to say I'm not the slightest bit upset by anything you say. Thank you for saying it. You reminded us that discovery, what the word discovery really means. It means finding things out you haven't thought about before. And that's the way it works. And I completely agree with your last slide. I just hope that the people who actually give us money will one day understand this.
Okay, let's thank Eric for the talk again. Next up, we have Carey Lisse telling us about solar system science with Axis.
Andrew, Tansu, and Eric for helping to introduce why solar system X-ray astronomy is important to a group of black hole and AGN enthusiasts. I'm going to explain, hopefully when you're watching everything, you're going to realize that our solar system is simply one of 100 billion solar systems in our galaxy. We happen to be living in it, so we can see processes right up close and personal. As you've just heard, our system was a protostar system about 4.5 billion years ago. It's going to be a white dwarf system in another 5 billion years, so we're middle-aged. Now, one of the things I'm going to hopefully hit over again and again is to be able to see processes up close that we can visit, that we can see that are low energy processes. And we can also bring back samples. So Andrew talked to you about what planets are made of. I have in my hand olivine and an iron meteorite, which is about 2/3 to 3/4 of the composition of our favorite planet, the Earth. I'm going to hand it around. And for those folks who like redshifts, while this is modern material, this is Z of 0.5 material. This was formed 4.5 billion years, about 10 billion years younger than the sun. That's all. So I brought show and tell to try and bring across to you what we're trying to do and why this is interesting. So here in a nutshell is everything we've seen glowing in the solar system, the X-rays, and we see it all over the place. We see everything from the moon and Uranus and scattered light in the surface of Saturn. We see Venus also is scattering. We see the Earth and Jupiter have very bright auroral emissions due to X-rays. So that's solar wind dumping on their poles. We see charge exchange from comets and Pluto and Mars, Io and Europa and Titan. So we're seeing lots of X-ray processes. These processes are relatively low energy. They're from megawatt to gigawatt compared to what you guys are used to thinking with AGNs and black holes. But you're also looking at things that are hundreds, if not megaparsecs away. These are on top of us, so we can see the fainter and more interesting and these interesting processes. If you want the elevator speech summary, what I'm trying to talk about is I just showed you a picture that we have over 20 different bodies in the solar system giving us X-rays. The physical mechanisms include just straight scattering of X-rays from the sun, auroral precipitation of the solar wind onto the magnetic poles of planetary bodies. Charge exchange, which I'm actually going to talk to and suggest that we really need to make sure when we're talking about atmospheric stripping, it isn't just due to photolytic stripping. I think charge exchange is really important. I need to bring that up and I want to emphasize that to you all. And X-ray fluorescence. I've mentioned aurora already. I showed you pretty pictures. Charge exchange I'm going to talk about for a little bit, but basically if you don't know what charge exchange is, there's going to be a slide. It's when a megakelvin plasma coming from the sun's corona, and thank you for stealing my thunder with the solar corona. You're going to see a slide in a second about a beautiful eclipse picture. Interacts with neutral gas. And basically, you have a very oxidized, highly stripped ion. It's very, can steal an electron from a neutral, which we can get close to. And in doing that, the electron will then rattle down in the receiving species and give off a characteristic S-ray. It is going to ionize the neutral, and that ionized neutral can then get picked up by the solar wind and get removed out of any sort of atmosphere, which is why it's important. And if I don't say it, I'll try and say it now. In cometary COME, we think that actually the charge exchange may be the dominant ionization source for the gas that's coming off a comet, not photolytic. So the big picture, we're going to try and look at all kinds of different mechanisms in the solar system, and we're going to extrapolate that and say the same things are happening in exoplanet systems because same chemistry and physics. And if you'd like a more detailed expert, I'll let you come back on the question and answer since I tend to talk long, but we're going to talk everything from solar wind diagnostics to X-ray effects on planetary bodies, the structure of our heliosphere, and by extension, astrospheres around other stars. We'll talk about giant planet magnetic hydrodynamics if you ask me detailed questions. Okay, it all starts with the sun. Sun is a 1 solar luminosity, 10 to 27 ergs per second in the XUV, just heard. So that's 1 part in a million of the sun's total luminosity. There's a solar wind that is coming off continuously. It's relatively faint compared to very young stars that Eric was just talking about. It's about 10 to the minus 13 solar masses per year, if I recall. But it has a characteristic composition. It's very heavy in CHOM, carbon, hydrogen, oxygen, nitrogen, helium particles as well. It has iron and sulfur and magnesium. It has all the major components that we see in the sun's abundance. And that allows us to actually tell when we're seeing X-rays produced by it. Here's my slide we're going to show. Here is a demonstration. You don't have to believe me. You can go outside just like you heard. Here's the sun blocked out. There's that beautiful megakelvin corona. And that corona, if you remember, if any of you experienced the actual eclipse, you might have noticed that the local color went from a yellow-white to an electric blue. That's simply the color temperature of the corona is a lot hotter than the 5780 surface of the sun. And from that corona, not only do you get X-ray emission, but you also get stellar wind emission. And every star in the in the galaxy has the same kind, has a corona, more or less dominant and important. The late type stars you heard about, talked about earlier, are actually fully convective, and they actually have more coronae proportionally to their optical emission. Here we have my pretty pictures again, and I'm going to walk you through a few of the most exciting ones. After I tell you that the total power, and this is an eye chart, it's included in the slide so you can read it at your leisure. In the oval, if you look in detail, you're going to find that all these different processes I just showed you are somewhere between a megawatt and a gigawatt in power. If you look on the right, I apologize, it's a little small, but I tried to put this on one slide, make it pack, is this is the energy of the emission processes versus the energy versus the optical emission from a body. And you see that the charge exchange separates out rather nicely from the scattered and the auroral processes. So we can characterize the different processes and what kind of power output versus the optical. For those of you who don't know about charge exchange, what you see on the left, let's see if the cursor works, is you have a highly stripped solar wind minor ion or stellar wind coming in, finds a neutral, it grabs an electron, it emits an X-ray photon as electron de-excites, and then heads off on its merry way and select one charge reduced. If you want to know what it looks like in terms of a comet, or you can think of this, or you can put your favorite planet there, like Mars. Solar wind's coming in, and O+7 comes in, hits and runs by a neutral, and it can be about 10 times the hard-sphere radius, grabs that electron and gives off an X-ray photon. Characteristically, you're about to see is when we looked at comets, we noticed, here's the sun's over here to the left, we didn't see the tail lighting up. We only saw an arc. So I'll go back and show you. We saw an arc in between the sun and the nucleus, which told us that the X-ray production was happening in an optically thick region between the sun and the nucleus. And that tells us that charge exchange is really, really important. It had been a scattering effect, and we also saw very, very little X-rays, if any, due to scattering. Here's our spectra from Chandra and from XMM of charge exchange from X-ray emission from comets, which, by the way, for all you people in the audience, I think is really bizarre. Comet's a kilometer-sized body that's maybe, if ice is in it, are probably 30 Kelvin on the surface. When it's near the sun, maybe 100 or 200 Kelvin. That's not X-ray emitting material. That's not a high energy process. The short answer is the sun's done all the work. The sun's made the megakelvin, highly stripped ionized plasma that's coming along and finding the neutrals. When we look at these spectra, we don't see scattering, we see charging. So that's telling you something right away that maybe charge exchange is very important compared to photovoltaic processes, and we should talk. And that's the reason why you want to look at solar system processes, which we can look in detail, because we can understand the radiation field and the stellar wind from the sun, and we can actually look over time and see what's going on. Let me give you a for instance. Here's Mars. So Mars is the target of the MAVEN mission, if you didn't know. It's this planetary mission that is actually today looking at the atmospheric loss rate from Mars. In a remote process, which we've shown you can do with X-ray, my colleague Conrad Dennerl has championed this, is we've looked at Mars with Chandra. And if you look, this is a detailed slide, I'm going to go very quickly. If you look at the day side versus the night side of Mars, you see an excess in X-rays in the day side. And that excess in X-rays is the right energies to be charge exchanged, not to be scattered. So we're seeing what looks like mass loss driven by charge exchange on the Martian day side, which is very interesting. Again, something you can do in the solar system. Give us access, allow us to actually watch the change over time over the solar cycle, and we can see this, hopefully we can see this loss rate change. And we can compare it to what MAVEN's doing. So we can, that's one of the nice things that we have a synergy with the mission that's actually at the planet versus what we can do in the X-rays. We can calibrate that, then hopefully we can bootstrap the exoplanet system. Let me talk about X-rays from Jupiter system really, really quickly. I hope this movie works. It doesn't look like it's going to. Is this the PDF or the, I guess it's the PDF. What you're seeing in these four captions is Jupiter looked at by ROSAT. And you're seeing both the poles and the disk light up. The disk is lighting up and scattering. The poles are auroral emission. As you go to harder and harder, higher and higher energies, only the poles show up. This is our best auroral map, and this was a beautiful movie showing you actually that the aurora just flips. It's incredibly time dependent. So staring at this for a bunch of kiloseconds would be very interesting and hopefully very demonstrative of what's going on exactly at the aurora. Let me point out that both Io and Europa, the innermost two Galilean moons of Jupiter, are X-ray sources. We think that's due to charge exchange as well. And then Io even has what's called a plasma torus. If this is Io, remember Io's got these huge fountains of sulfur dioxide throwing up. These fountains are 10 to 20 to 30 kilometers tall. The sulfur oxides in those fountains get ionized by solar UV coming in, and they get picked up. And remember, Jupiter is a huge E cross B engine. It is rotating 10 hours. It's 10 times bigger than we are. It's got incredible magnetic and electric cross fields, and any ion gets picked up and really energized. So it gets thrown into this torus and then gets dumped on the poles of Jupiter. All of those create incredible. Let me move on. If you want to bring this to what AXIS can do, Jupiter is pretty big. Jupiter is somewhere between 30 and 50 arcseconds. And just to give you an example, what AXIS plans on doing with PNEs, so planetary nebulae, Jupiter is going to be a wonderful case study for AXIS to go after. I'm going to talk about low-hanging fruit, and this is where I'm hopefully not doing too badly on time. There's a lot here, and this is where I'll talk and we'll take conclusions. Things we could do in the solar system that would be useful science for not just the solar system. I've already talked about studying the solar X-ray induced chemistry and stripping the planetary atmosphere. So we basically want to focus on Mars. We want to attain high spatial resolution elemental composition of surfaces of any atmosphere-less spot. So any body that it does not have an atmosphere. And that can be Ceres or Vesta or Io, Europa, and Enceladus. There have been many missions to the moon, for example, that mapping the surface of the moon in X-ray fluorescence. If we can study them in X-rays with AXIS, go deep, and even get some spatial resolution, we can make maps of composition of the surfaces. I mentioned we want to understand the KeV to MeV hard emission from Jupiter's poles. We want to understand how material can come off of big fountains on Io and be dumped on the poles of Jupiter, and wind up making both soft sulfur and oxygen X-rays, as well as all the way up to MeV gamma rays. And lest you forget, people have discovered gamma emission from thunderstorms on the Earth. You can make, with rather prosaic mechanisms, you can make high energy photons. We'll talk about, well, we'd like to learn why the North Jovian pole doesn't seem to be the same as the South Jovian pole. We think they'd be connected magnetically. I mentioned the Io plasma torus, which is really interesting. And we think it's sourced by neutrals and gets ionized and then gets dumped on Jupiter. Well, if you don't know, Saturn has a moon called Enceladus. It's been rather famous. It's the one that puts out the water jet. And there's something called the E ring, which is sourced by Enceladus, which is basically oxygen and hydrogen atoms, which then get ionized, and they should get dumped on Saturn's poles, but nobody's seen their effects yet. We want to go and see if we can find the Saturnian aurora. Again, we have another Jovian. It should have X-ray emission just like Jupiter. We haven't seen proof of that. I'm going to skip over that one. We'd like to see the first X-ray emission from Neptune. Uranus has barely been detected by XMM. We expected also to see it from Neptune. And we would also like to follow up on my purported observation, and I get laughed at by my New Horizons colleagues, 7 photons from Pluto. This group will not laugh as hard because they understand that detections can be very, very few photons. And we found out with Chandra, we argued that it's the wrong energy range. It looks like it has to be charge exchange. And if so, it has to be charge exchange actually in a column, not just around Pluto, but in its tail. We'd like to follow that up with AXIS, determinant. And the reason why that's important rather than just nominal interest, we like to stare at everything in the solar system, look for X-rays. You can detect atmospheres around KBOs if you can get to X-ray emission to do the charge exchange. Remember, you need neutrals, you need the solar wind. Solar wind's already on, always on. If we get X-rays around Eris or Makemake or Parwar, some of the other KBOs, we'll know that they have a neutral gas around. We'd like to confirm, we'd also like to get the first ever X-ray color ratio map, so cometary charge exchange. I showed you that image of charge exchange. Remember, it looked like a sickle. Looked like it was a optically thick or to charge exchange emission region in front of the coma. Well, we've always been X-ray starved, and I should say, if I've forgotten to say it, everything we've done in the solar system so far has been X-ray starved. We can absolutely use 10 to 100 times more photon in all our images. If you gave me an X-ray color map, and remember, I'm arguing that it's optically thick. If you start with an oxygen +7 at the top of the coma, it should go to oxygen +6, and then oxygen +5, and then it doesn't give you any X-rays anymore, it's giving you UV. We've never been able to prove that simply because whenever I try to get enough statistics in my pixels, they always get really big and fat, and I just have the ratio goes to half. If I could stare with AXIS at a bright comet and just simply get and actually watch the progression of charge exchange through the coma, I could learn an awful lot about the process and see if we know what we're doing. The other thing is that's really quick. I'll say real quick. If you can get if you can stare at the X-rays from a comet and you can see where they suddenly start, you can get where the bow shock is of a comet. You can learn a lot about the comet and how it's following through the ISF. And that's a really important diagnostic. Finally, I'll say we can also track the motion of flares and CMEs moving through the heliosphere. There's been a bright idea that if we see a CME, you've heard about those, that's a giant ejection from the sun. usually comes out of the poles, and it should light up different objects and with charge exchanges that move through the solar system. We can actually watch it propagate. The other thing we could do in that respect is that if we can look at comets, we can use them as standard candles. I've talked a lot about how comets give up charge exchange, and we think we understand what kind of X-ray luminosity they have. What we can't do is we can't send missions to the heliosphere that are like 10 or 100 AU straight up above the ecliptic plane. We can send them out along the ecliptic plane, but we can't send them up. But instead, what we could do is use the X-ray emission from comet to actually map the heliosphere. One thing that didn't make on this list, I apologize, I'll put it in real fast. There's been a very bright young man named Sam Cabot who argued that next time we see a Oumuamua, that if we were to actually have looked at Oumuamua or Borisov in the X-ray, we could have detected charge exchange due to the gas, or if it had gas, and if it was actually, if you remember, there were lots of arguments about whether Oumuamua was active, and that gives you the non-graphs. We could have detected neutral gas around Oumuamua totally independently of everybody else and all other techniques. And we could have done it relatively sensitively. So there's a wacky but crazy, but we actually have a TOO from XMM in right now. It would be a heck of a lot easier if we could do that with AXIS, and we actually probably could image the X-rays around 3I, the third interstellar object, which we're waiting on. With that, I think I'll stop. The last thing I will point out on this list, you'll notice that AXIS can support many of the current missions. I already mentioned Maven. Europa Clipper and JUICE, when they get to Jupiter, are going to be would be very much helped by AXIS measurements of the system. The ESA Comet Interceptor mission is going to happen, I think, in 2028 timeframe. And also Uranus Orbiter Flagship mission would be also greatly supported by AXIS observation system. So I will leave this slide up in case you're wondering what this will cost you, because nothing's for free, can't stop it. This is the kind of things we would like as a solar system group, and I will stop there and take questions. And thank you very much. I want my meteorite back.
Okay, let's do maybe one quick question.
This is not a question, but I need to mention something. A very good place to look for charge exchange are novae. In the high resolution spectra we obtain with the LETG, even with the RGS, we find clear evidence of charge exchange. And this PhD student Behar is actually writing his thesis on charge exchange. The spectra are really beautiful, and it's a very good place to learn about it. The student's name is Sharon Mitroni, and we will be looking for postdoctoral positions soon. So
thank you. And let me answer that with a comment. I forgot to mention this. Charge exchange happens, we think, wherever you get millikelvin or megakelvin plasmas, highly stripped hydrogenic, heliogenic ions encountering neutrals. Well, one of the natural places for that, which you guys are not going to laugh, but our physics folks have been kind of discovering this last decades, is at the edge of the heliosphere. Yeah, you have the stellar wind plowing into the neutral cold ISM. So they have all their current models now are based on fulcrum, if not one, two, or three different hydrogen atom comes in, it charge exchanges multiple times across the heliopause and the helioshock. That being said, remember our sun is one of 100 billion stars. Every single star with a stellar wind is going to have charge exchange at the edge of its astrosphere. That means there should be a background component to our galaxy in the soft X-ray that we should be able to sum up and see. And this is the kind of thing that we've discovered, or we're actually, if you will, promulgating and researching more by doing solar system astrophysics. Thank you for the question and reminding me to say that.
Okay, let's thank Carey again. So next up, we have the poster lightning talks. I believe we have 5. So if we can get the speakers to come up. And each will have 2 minutes.
Okay, does everybody see their poster up there? If they know they have it. Everybody's good? Which one is yours? Yeah, I'll show them. You show them, or that's my own.
Hi, my name is Chao, and I'm from George Washington University, and my poster is about using machine learning classification to classify X-ray source, and with a big focus on the X-ray galactic planet surveys. So what our group have been doing basically is using machine learning to classify this X-ray source that is unknown to us before. We don't know what they are, and since there's a lot, there's like hundreds, thousands of them, with using this machine learning method, we can classify them very quickly. And on the left, we basically an example of this kind of classification where we try to classify X-ray source in the field of gamma ray source so that we can try to understand the nature of that gamma ray source. Now, with doing this kind of machine learning classification, we also need good multi-weighting counterparts. And on the right-hand side, we have counter examples of a bad multi-weighting counterpart match. That's from a Chandra source that is very off-axis. So the positional uncertainty is very large, and that matched to like 5, 6 multi-weighting counterpart there that is labeled with the 1 and 2s. And with the axis, we'll be avoid this problem because axis has a very good PSF that is all across its field view and also has a better effective area, and that will allow us to localize those multi-weighting counterpart much, much better. Now, since we're also doing machine learning, we have produced training data sets, and you are welcome to check it out in our posters. And even though we as a group is more focused on compact objects, there are also plenty of AGN here for your AGN folks. Thank you very much.
All right. Hi, my name is Seth Gagnon. I'm a PhD candidate at George Washington University. And in my poster, I'm presenting some preliminary results of a population study of pulsar wind nebula. So we're specifically focusing on the uncooled spectra that we measure with Chandra in X-rays, obviously. And here I'm showing the central plot of my poster where I'm exploring the correlations between the observed X-ray morphology, the multi-wavelength light curves, as well as the measured X-ray radiative efficiencies. Here I'm showing some correlations between a couple other parameters. So in the top plot, you see the pulsar and pulsar wind nebula photon indices, and in the bottom plot, the pulsar wind nebula photon index and the radiative efficiency. So in blue, I'm plotting the Chandra data points, but obviously this is the AXIS conference, so I want to show how AXIS can help propel a population study like this. So I simulated some AXIS data points, and I show those in red. If you'd like to hear anything else about this or have any questions, please come visit my poster.
Hi, I'm Laurel. I'm a grad student at MIT working with Mike McDonald. I'm a clusters person, and I'm particularly interested in what Axis will be able to do for us in terms of looking at cluster evolution and being able to push out to really high redshifts in kind of the era of galaxy cluster formation. But to that end, in order to understand how the high redshift universe looks different from what we see in our local universe, we obviously need a good understanding of what's happening at low redshift. And so we've been doing some work on an SC selected sample of low redshift galaxy clusters. We think this is kind of the best that we can do in terms of eliminating bias in putting together a cluster sample at low redshift. And so all of these we've followed up with Chandra, and we're starting to do some population level kind of statistical analyses. And then we also expect that there will be a handful of interesting systems within this sample. So one example is Abell 1885, which we observed last year, and it stood out to us because it has an X-ray bright point source at the center, which we've attributed to a highly accreting AGN. And if you look in the radio, there's no evidence of large-scale mechanical feedback. So we basically determined that the AGN is kind of at the point in the cycle where it's just turning on. But if you look at the ICM, you actually notice large-scale suppression of star formation. And so that points to a decoupling in timescales between the duty cycle of the AGN and the energy dissipation in the ICM. And so we've been able to do some stuff with a short Chandra exposure, but we're looking at, we're going to be doing a much longer Chandra exposure to be able to more deeply probe the ICM. So this is a really good example of something that Axis will do really well. And in particular, if we want to do this kind of study at higher redshift, that'll be a great use case for Axis.
So hello everyone. I'm Shinjalin. I'm a graduate student at the University of Kentucky working with Dr. Yuan Su. Today I want to bring you to a much larger scale to galaxy cluster, in particular to look at a phenomenon called sloshing cold front, often found in the full cold clusters. And we focus on one of the ancient sloshing cold front found in the Virgo clusters, and we using the XMM Newton's observations to detailedly study this, the third cold front found there. We measured their temperature and their surface brightness, and we found an indication of Kelvin-Helmholtz instabilities. And this is really important for us to understand the Kelvin-Helmholtz instability to better probe the microphysical condition of the intracluster medium, and also understanding what kind of transport mechanisms in play in the ICM. And of course, with Axis, it's superb PSF and the effective area. If you look at the simulated image there, we can actually already see some of the KHI features there that allowing us to better constrain these different mechanisms, the transfer mechanisms in the ICMs. So if you're interested in learning more about the sloshing cold front and you want to discuss how Axis can actually push the boundary of the field of the galaxy clusters, feel free to drop by my poster. Thank you.
Hello, everyone. I'm Hamta Farouki, a PhD candidate from Washington University in St. Louis. And my poster explores the potential electromagnetic radiation from binary black holes embedded in AGN disk, specifically 511 keV emission from positron annihilation. So the idea, as you can see in the picture, is that once these black holes merge in the AGN disk, the remnant black hole gets this recoil kick and emits, it creates matter from its surrounding, and then under some specific circumstances, it can lead to the emit or launch of the Blandford-Zonai jet, or even if there's no jet, there still will be super Eddington accretion, which can lead to high energy radiation and possibly positrons. So what I have done in my research is that I estimated the amount of positrons created in these environments and using analytical expressions, and calculated the annihilation and 511 keV flux. And we found that under some optimistic conditions such as high binary black hole mass or dense AGN disk, we can detect them with COSI. So yeah, your question might be, how is it related to access? That's my question too. But yeah, with the help of access, actually it can have these complementary role, and with the help of access, we can localize and characterize these low luminosity AGNs where these binary black holes can exist. So with the help of access and COSI together, we might be able to find these black holes, hopefully. So yeah, thank you so much for your attention. Yeah, my poster is outside, and I would love to chat more with you. Thank you.